we're now going to look at the idea of continuity and continuous functions. And this is another important concept in calculus. If a function is continuous, then it's a very nicely behaved function, and there's a lot of things that are true about it that are very useful here. So here's the definition here of a continuous function. So a function is said to be continuous at x equals c, given that the limit of f of x is x equals c is equal to f of c. So in other words, the graph is approaching the actual value of the function at that point. So a good way to really understand this definition is to look at the different ways that a function could fail to be continuous. So one way is if the function does not have a limit. So let's say we had a function here that went like this. Maybe it was like that. And this is y equals f of x. And so if this is x equals c here, at c, the graph actually makes a jump, and in this case there would not be a limit. So as you approach c from the left and as you approach c from the right, it's approaching two different values. So one way then that it could fail is if the limit as x approaches c of f of x does not exist. If it doesn't exist, then you don't have a continuous function. The function is not continuous at c. And of course there's other ways that you can not have a limit here. It doesn't have to be a broken hole in the graph. It could be a vertical asymptote with the graph going off into infinity. It could also be where the graph oscillates up and down forever, like sine of 1 over x. So the point here is if it doesn't have a limit, then it can't be continuous at that point. Okay? But there are situations where the function does have a limit here. So let's say I have this function that goes like this. And here at c, okay, in this case, as you approach c from the left and as you approach it from the right, it does equal a certain value here, right? So what's the problem in this case? Okay, so it has a limit, but f of c is not defined at this point. And so what you have here is a hole in the graph. So if f of c is not defined at that point, then the function will fail to be continuous as well. Okay? So, but you could actually have a limit and the function could be defined at that point and it still not be continuous. So let's see why this is. So let's say you have a hole here at c, right, and it's approaching L. Okay, but let's say at c the function is defined to be this point right here. This is f of c, right? So here it has a limit and f of c is defined. So what's the problem in this case? The problem would be that the limit as x approaches c of f of x does not equal f of c. Okay? And so what does it mean then for the function to be continuous at c? Well, it means that the function here at c, right, that it has a limit as you approach c, right, but the function is also defined at that point where the limit is. So in other words, I'm like taking the graph and instead of having the function be defined up here, I'm moving that point and filling in the hole in the graph. And in that case, then, it is continuous. And the reason is that the limit as x approaches c of f of x is equal to f of c. And what you have here is one continuous curve as you go through c. So that's the idea. That's what it means for a function to be continuous. Okay. Now, continuity, the technical definition, it's defined at a point. Okay. So when I say this function is continuous here at c, here, what I'm saying is at that point it is continuous. Okay. So, but in general, if the entire function is continuous, then what it means is, excuse me, that the function is continuous at every point in its domain. Okay, so all the points in the domain are continuous. So you actually define continuity for a given point, but when you say that a function is continuous, then it means that it's continuous at each point in its domain. And then there's a lot of nice functions that are continuous. So for example, any sort of given polynomial, you know, these are these curves, maybe like this, okay? The point here, the kind of the intuitive idea is that it's this unbroken curve, and you could trace out the curve without lifting your pencil from the paper. If you can do that, then it's a continuous function. Notice any of these, I wouldn't be able to do that. Here, I'd have to lift it up, right? Here, in order for there to be a hole, I'd have to lift it up and keep going. For here, I'd have to lift it up, go up there, and then keep going. But here, I can trace out the whole curve without lifting up my pencil. Well, polynomials are like that. They're nice functions that are like that. Other functions are like the sine and cosine wave. Okay, so a wave like this. Now I lifted my pencil up there, but if I started way down here, you could keep drawing the curve. And you got this one unbroken curve forming that wave. And so those are continuous at every point. So this here is actually the formula for a semicircle with a radius of 2. So it would go up, come up here. Okay, and its domain is actually -2 to 2. Okay, so now the question is this function continuous? Is it continuous at every point in its domain? Well, technically, according to this definition, if we just limit ourselves to that, it wouldn't be continuous at these endpoints, right here and here, because technically the limit wouldn't exist because the function isn't approaching the same value from both sides. On this side here, so as you're approaching from the negative side, or here as you're approaching from the positive side, the function's not defined. So technically the limit doesn't exist there, but the one-sided limits exist. So in other words, the limit as x approaches -2 from the negative side of f of x, you know, that limit's equal to 0. And then the limit as x approaches +2 from the positive side. I'm sorry, I actually mixed this up. This is from, as you approach -2 from the positive side, this is 0. And then as you approach +2 from the negative side, so from this side, so this is a negative of f of x, this is equal to 0. So the one-sided limits at the endpoints in the domain exist. And then for everything else, so the limit as x approaches c of f of x exist for all the values, for all c here, that's strictly between -2 and 2. So like in this open interval. So in the open interval here, it's continuous. And then at the two endpoints, it does have the one-sided limit coming from the domain on either side. if that's the case, then we would say that this function is continuous. Okay, as long as it's continuous there, as long as it has these one-sided limits there. Okay, another good example is like tangent of x, right? So we have, here's 2 pi, negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2, pi, pi over 2, 3 pi over 2, so this is negative pi over 2, negative 3 pi over 2, pi over 2, and then 3 pi over 2. So tangent here has these vertical asymptotes. Okay. And there's a vertical asymptote there. And so if I consider just the interval, so if I am just interested in one piece, one cycle of the curve, the domain for that one cycle would be negative pi over 2 to pi over 2, right? And it wouldn't include the two endpoints. So it's that open interval from negative pi over 2 to pi over 2. And on that interval you have, I could draw that one curve. It's one single unbroken curve. So the tangent for any one of those cycles is continuous. And actually over the whole domain, if we don't include those endpoints, for each of these it would be continuous. It just is undefined. It doesn't have a limit at those points. And those points also are not in the domain of tangent of x. So as long as we're careful at those where those asymptotes occur, then the tangent of x would be continuous. Okay? So this is the idea of continuity. We technically define it for a point, and it occurs when not only the limit exists, but that the value of the function is equal to the limit at that point. And then we would say that a function is continuous if it is continuous at each point in its domain. And we could also, if a function is not continuous at each point in its domain, we could consider the function over some interval where it actually is continuous, and then we could say that function is continuous over that particular interval. Okay, and we would be safe then. On that interval, we know the function is continuous. So that's the idea of continuity. So in the next video, we'll learn some of the properties of continuous functions and how we can use that to identify when a function is continuous or not.